Flow is one of the most important process variables in almost every industry, whether continuous process, batch, or hybrid, from bottling to chemicals to water wastewater. Hi, I'm Walt Boyes, editor of Control and ControlGlobal.com, with another Back to Basics in Flow measurement for the Process Automation Media Network. This edition is sponsored by Endress & Hauser. Endress & Hauser is a leading supplier of measuring instruments and automation solutions for the industrial process engineering industry. Now, today we're going to talk about two of the most important types of flow meter, turbine flow meters and electromagnetic flow meters. So let's talk about turbine flow meters first, since they are the oldest of the velocity sensing or volumetric flow meters. Invented in the late 1700s, yes, that's right, the 1700s, by a guy named Waltman, the basic structure of his meter looks very much like a turbine meter of today. There's a rotor, which turns with the flow. The speed of the rotor is proportional to the velocity of the fluid going past it. Waltman used mechanical gears to get his signal to the register, just as most turbines do today in the water and wastewater industries. Turbines are not positive displacement flow meters, however. They're volumetric, and their measurement is based on velocity. But they are extremely accurate. Some designs, even the mechanical meters, can be used for custody transfer in water, hydrocarbons, and in gas flows. Turbine flow meters can be found in aviation fuel metering, natural gas pipelines, specialty liquids in the chemical industries, in the food and beverage industries, and in medical applications too. Turbine meters come in all types, including propeller meters, paddle wheel meters, impeller meters, but they all work by converting the rotational energy of a spinning prop to velocity-based volumetric flow. They can have entirely mechanical designs, be electromechanical hybrids, or have solid-state sensors picking up pulses from the rotor as it spins. Turbine meters are sensitive to temperature and viscosity of the fluid and to fluid density. And they're also highly susceptible to fouling and should only be used on clean fluids and gases. Particulates, rocks, bottles, and rags immediately foul the prop, and the meter must be repaired. Also, as Dr. Flowmeter says, overspinning the rotor by putting a higher flow rate than it was designed for may cause the rotor to break, and you're going to find it downstream somewhere. Turbine meters also have a size limitation. It's very difficult to make a turbine meter much over 12 inches or 305 millimeters in diameter because the rotor becomes huge and its own mass interferes with its ability to spin. It takes a lot more velocity to spin a really big rotor. Insertion turbine
Smith Meter G-Series turbine meters are an excellent choice for the custody transfer of low-viscosity refined products, such as LPG, gasoline, and diesel. They deliver high-accuracy measurement over a wide range of operating conditions and are a cost-effective solution for refined product pipelines and marketing terminals. This is especially true in terminals where multiple product blending is required. Turbine meters are inference-type meters that determine the measured volume by inferring the fluid velocity over a fixed cross-sectional area. As the G-Series meter housing is cut away in this animation, we see a cantilever-type design where the multi-bladed rotor is supported by an upstream stator. The stator also channels the flow stream, depicted by the flowing blue arrows, through the rotor. The rotor is hydraulically balanced and floats on a virtually frictionless, highly polished tungsten carbide bearing. The rotational speed of the rotor is directly proportional to the axial flow velocity of the fluid. The rotor has a number of equally spaced blades that are made up of a paramagnetic material. A pickup coil is located directly above the rotor and is completely isolated from the fluid. It is constructed of many coils of fine wire that are wound around a permanent magnet. As each blade passes underneath the pickup coil, it passes through the magnetic field. The continual passing of the paramagnetic blades under the coil induces an AC voltage in the coil, which is seen as a sinusoidal wave. The sinusoidal wave is then converted by the preamplifier into a square wave pulse stream, as shown. Since the flow area is constant and the rotor velocity is directly proportional to the flow velocity, each output pulse represents a precise amount of fluid that has passed through the meter. The continuous pulse stream is then transmitted to an electronic counter or flow computer to indicate both instantaneous flow rate and total metered volume.